Welcome. In this video, I want to share a lecture that I gave for a course that I taught on object-oriented programming and design with C++. The subject of this lecture is polymorphism. If you come here, just found this lecture on your own, one thing I suggest is for you to go back and check out the other lecture I posted on inheritance, because the contents of this lecture are exactly right after in the inheritance content. Now, if you already feel like you have inheritance down, you understand it, you don't need to go over it, then go ahead and watch this instead. But if you don't, I strongly encourage you to check out the inheritance lecture. I'll post a link, I'll leave a note right here so you can click it if you want to watch it. All right. With that being said, I hope you enjoy the video, but most importantly, I hope that you learn something new. So we have some private members, which are the data members. We have some protected members, which in this case was breathe. We have access to it by animal and any of the derivations. And then we have access to, by anyone, the eating function. We have our dog class, which inherits from animal, has breed, it can bark. We have some constructors. I don't put the constructors and the getters and setters generally in PowerPoint because there's not enough space for me to write them here, right? But we added them in the code. Okay, so having these classes, we can do what we have been doing with them all the time, right? What have we been doing with them? We have been able to create instances of those classes. It's what we have been learning to do. So I can create a variable, right? And I can call the variable whatever I want. So I just call it variable name. You can put appropriate names here. And that variable name can, it's of a type animal, right? So this variable is of type animal, which means that this variable can only contain instances of the class animal. So then I create an instance, I create a value of type animal, and I put that animal into this variable, right? And then so this is me creating an instance of the base class, right? And then I can say, well, you know what? Let's actually create an instance of the derived class. So now I have another variable, right? We call it whatever we want to call it. That variable is of type dog. So that means I can put dog instances in it. So then I create a dog instance and I put it in there, right? So even though you have a base class and a derived class, you can very easily use either of them. So if I just care about a generic animal, I can just say animal, my, let me move this keyword, my animal. And then this is going to be what? Animal. And we need two parameters, an age and a weight. Well, let's say the age is going to be a 10-year-old with a 50-pound animal, right? So I have created a generic animal, and everything about this animal would just be these members, and I have access to all the public members. My animal that get age, right? So I can simply create the generic version, the base version of this class, and I can also go and create an actual dog, and the dog would actually be what? Dog, my dog, and this will be a dog that I can use one of these constructors. Let me move this here. I can either use the first constructor, the second constructor, or the third constructor. So let's just leave it as the second constructor, which would be from my breed, I want a Labrador, which weighs 65 pounds, let's just say, right? So now my dog, if I do dot my dog, I have the functions that are available to it. So the bark and the get breed, right? And so now I can create either an instance of the base class, or I can create an instance of the dog class, right? So this will be like bark. So this is what we have been doing so far. Nothing new, nothing fancy. You don't have to create an instance of the derived class. You can create an instance of the base class, right? So just putting it out there. But we get one more thing. Now, let's talk again a little bit about variables, which you probably, you know this, but I'm going to repeat it so that maybe if it hasn't clicked, it clicks even more. So we create variables and assign a value to them. That's what the whole point of variables are. A variable contains a value in it, right? And we care about that value. That is information. So here we have a variable of type integer, right? What kind of values can I put on a variable of type integer? Well, I can put integers. So I can put a 10. Why can I put a 10? Because this value, this 10 is an integer, right? This 10 is an integer. So because this value is an integer, I can put it in an integer variable. right? It just makes sense. Now, we can do that with enumerations. Here's an enumeration of some variable, that whatever we call it doesn't matter. And then this variable, it's of type breed. Breed is our enumeration, right? And then I can assign a value to it. What kind of value I can assign to it? One of the options in our enumeration. Well, one of those options is Chihuahua. So why can I assign Chihuahua into this variable? Because Chihuahua is a breed, right? If I did Labrador, Labrador is a breed. So I'll tell you one more time. I can put this value into this variable simply because Chihuahua, the value Chihuahua, is a breed. Then we use the same logic with objects. So I have another variable. This variable is of type dog, right? So it can hold what? It can hold instances of the class dog. So here I call the constructor and I create an instance of the class dog. And I can put this instance into this variable. Why? Because this dog instance is a dog. I'll say it one more time. The value dog, this instance that has been created, is a dog. Therefore, it can go into a dog variable. It makes sense, right? I mean, it sounds kind of silly to even say it, but it's very important. And I keep saying, is, and it should prompt you the is a relationship, right? A 10 is an integer. A Chihuahua is a breed. A dog is a dog, right? So obviously. So because we talked about the is a relationship and we see how these values get assigned into their proper variables, because is a relationship is a thing, even with these regular values that we don't even think about it, we get something special. So a variable of type dog can hold a dog instance, right? Obviously, because a dog is a dog. Okay, that's okay. The dog inherits from animal. Why? Because we mentioned on the last lecture that the dog and the animal have a relationship. And that relationship is that a dog is an animal, right? A dog is an animal, which means what? It means that a variable of type animal should be able to hold a value that is a dog instance, right? Because a dog is an animal. So that means that if a variable like this one on here is of type animal, it should also be able to contain a dog, because a dog is an animal, right? And this is where things start to go crazy. So now we can tell the C++ language, we can tell whether a derived object should be viewed as a base object by the public. So what I mean is this: if I have a dog, right? A dog is an animal, right? But if I tell you, hey man, can you take care of my dog? You just have to feed him and play with him a little bit. And you're like, all right, I can do that. Now imagine that instead of saying dog, I say, hey man, can you take care of my animal? You can just feed him and play with him a little bit. You'll be like, well, what kind of animal is it? Like, what if you're bringing me an elephant or something, right? I mean, if someone has an elephant pet, that's pretty cool. But the point is that how you view the same object, it matters, right? I can say a dog, I can say an animal, but if I tell you one or the other, your perspective of that will change. So perhaps you want to limit the C++ language to say, hey, no, only view dogs as dogs, period. Don't view them as animals, because then people will get crazy and think that we're talking about elephants. So only treat dogs as dogs. That is a default behavior of C++. C++, and I think in any other language for that matter that has an object-oriented programming paradigm, will treat inheritance as, no, you intend to only use dogs as dogs, not dogs as the generic version, right? So in our previous lecture, we talked about Chrome and Firefox. What I'm saying is Chrome is treated as Chrome. It doesn't get treated as a browser, right? A table doesn't get treated as a surface. It gets treated as a table, period. However, sometimes we would like that treatment to be available. I would like to say, you know what? Treat my dog like you would treat any other animal. Or you know what? Treat this table like you would treat any other surface. Treat this Chrome as you would treat any other browser, right? So we can say treat that specific instance as its generic version of it, right? So now I can do that, and I can tell C++ when I want that to be done. And I do that by simply saying, the way I say it is I have my class dog, which inherits from animal, and I want it so that if the public, here's a keyword, if the public wants to see this dog as an animal, that's okay. So this means, no, dogs are dogs, period. This says, hey, a dog is a dog, but also you can treat it as an animal, right? That's what this little public keyword does. And that little public keyword causes a whole new level of things that we can do. So let's talk a little bit about those. Look at this line of code. I have a variable called my dog. What is the data type of this variable? It's an animal. Well, I can put a dog into an animal variable. Why? Because a dog is an animal, right? So this is very powerful, right? And let's just go show it, right? So here let's first we should go here, and we're going to go back to our dog class. Where's our dog class? And notice that when I put dot, I only got bark and get breed, right? Because these are the things that are dog related, right? But now let's just say that I want this to be treated as an animal, publicly speaking, right? So I would say public animal, right? So now a dog is also publicly an animal, right? So before, a dog is a dog, period. Now a dog is a dog, and also the public gets to view it as an animal. So now that it is an animal, right, when I do the dot, I get all the other things. I get bark, I get eat, I get age, get breed, get weight. I get everything about the dog plus everything about the animal, meaning the public. Who's the public? The public is where you put that code that gets to call the public function members, right? So right here, this is the public. This is outside of the dog class. This is outside of the animal class. So the public says the public can view this dog as an animal by simply putting this keyword, which means that now everything public to dog and animal is available because you view the dog as an animal. If before it was like, no, you only view it as a dog, you only get the dog stuff, right? So that's why putting public here, we get access to all the other things that we didn't have earlier. Now, what I said was that this is powerful because here we have get age, right? Dog, my dog get age. And so we have an animal that is put into an animal variable. Here we have a dog that gets put into a dog variable. That's obvious. But then what was not so obvious that we get to add is I can actually get the dog value that I have created and assign it into an animal variable. And that's perfectly fine, right? So this is saying you can treat dogs publicly like animals. Okay, this dog will be treated publicly like an animal. So a dog is an animal, so a dog gets put into an animal variable. I could not do this actually. So someone asked, you couldn't do this before adding public. The answer is no. It is very easy. Take this off. Hey, conversion to inaccessible base class, right? So C++ knows, Visual Studio knows. It's like, hey, we know that that's the base class, but that's not accessible. We don't have access to it. It's private. And in fact, having nothing here is the same thing as saying private, right? So if you wanted to explicitly say private, you could do that. However, remember, even with our data members, if we don't put the label, by default, it considers it private. So by not putting the label, it considers it also private. However, if you want to be able to do this thing, we have to say that the dog should be able to be seen by the public as an animal, which therefore now I have a variety of things that I can do. No, actually, it should not. If I put private, so if I put private, it's just how Visual Studio sometimes, if I go to this file and I do changes, sometimes the error goes away, but it's just a little, it's not really a glitch, but it's just that since you're still editing text, sometimes it's like, oh, maybe the error went away, or no, it didn't, etc. So yeah, so we have to put the public keyword to be able to do this. If we don't put the public keyword, we get nothing new. Basically, the whole polymorphism kind of basically, if you don't put public here, you don't get polymorphism. Okay, I haven't really thought about that a whole lot, but I would say that if you don't say that this can be a public treatment, the whole aspect of polymorphism kind of disappears. I would not say all of it, but a good chunk of it would disappear. I would have to think about that question that I just came up, is what would happen if you never make any inheritance public? You would probably not get the power of polymorphism. But now this right here is very powerful. And you might say, well, okay, dude, like you just put a dog in an animal variable, right? I could have put a dog in a dog variable, and that's it, right? Why are you making more? Why are you teaching us more things just to make us, you know, to give us more assignments? Well, that's not a bad idea, but still, that's not why. There's actually a lot of power in this line of code, and let's see what I mean by that. We can now use a animal variable to hold a variety of animal instances. So here, I create a variable called my animal of type animal. I go and I assign a dog instance to it, and it goes here, right? And then later I'm like, okay, I don't need the dog no more, and I get rid of it. And I go and now I can assign a cat instance to it. I don't need it anymore. I now need a giraffe, and I can assign a giraffe instance to it. With the same variable, I can hold a different set of animals. And that's, if you don't see something crazy on this, I'm either it hasn't clicked or something's wrong. But the point here is that I can use the same variable to hold a variety of different animal objects. So here, this my animal, I can leave it as is, right? So this will be a dog, but I can say, you know what, forget the dog. I'm just going to now change it to a cat, and the cat is going to be 10 years of age and 25 pounds, right? And also, we have to make the cat public, right? So let's make this public. And now, look, the same variable, the same function usage. I did not change anything about this, and now I'm using a cat. How cool is that, right? I don't even have to change this variable data types, right? It automatically knows that, well, this is an animal, and I'll treat it as such. So here we go, get age. So this is powerful. Now, okay, you might say, well, dude, that's okay. And the whole idea of polymorphism. So someone says benefits functions that don't know what animal you might send. Yeah. So if you had a function that only cares, let's say you had a function, let's say down here. So you had a function void display animal age, right? And then you have an animal, some animal. Well, this function does not care. This function does not care if you send in a dog, a giraffe, an elephant. It doesn't matter. You could send whatever you want to it. It's like, I only care that I need the age of that animal. So I can just say cout. Well, actually, yeah, I would say cout. The age is, and I just say some animal get age, right? I can just do that. And then I can pass that to that function, display animal age, and I pass my animal, right? And then if I run this is actually a good example of that. So here is, if I run this, here's the age is 10, right? And if I suddenly say, you know what, no more cat, I want dog, and this is going to be breed, I'll go back to Labrador, and let's just say that. So it will default to an age of 0, and if I run this, age 0. I did not have to change the function, right? This function worked for dogs, it worked for cats, it's going to work for elephants, it's going to work for lions, it's going to work for anything that fundamentally at the base level, at the generic level, is an animal, right? So that's one of the powerful things about polymorphism. And we call it polymorphism because this animal variable, at one point it was a dog, at another point it was a cat, at another point it was a giraffe. So it has taken many forms, right? It's not always the same thing. When you have a dog variable and you always assign dogs, even if the dogs are different, it's still a dog, right? So it hasn't taken different forms. But when you're able to put different instances from derived classes into this base type variable, you have many different forms, many different things that it can be. What if you put dog as a parameter? So you mean dog here? What if I put dog here as a parameter? Okay, so if I put dog here, I can only send dogs. Now, remember the little analogy I said earlier. If I said, hey, can you take care of my animal? You would probably want to ask me, hold on, what kind of animal do you have, right? You would want to know that, because you cannot assume that I'm talking about a dog. An animal could be a variety of things. But if I say, hey, would you take care of my dog? Maybe you're like, all right, that's fine. I've taken care of dogs before. That's okay. So this function, you can think of it as that function. This function says, hey, you can give me a dog, but only dogs, which means if you try to give me a random animal, I'm not going to accept that. In fact, this is an error, right? It's saying, hey, you're trying to give an animal, but the function takes a dog. And the function, even though it's a dog, right? This is a dog. This is a dog, but we're treating it as an animal, which means that when I use it in the function says, no, you're giving me an animal, and I don't know what that animal is. It could be a dog. If it is, great. However, I don't know. And because I don't know, I will not accept this animal. I will only accept a dog. So if you want me to take your dog, don't call it animal, call it dog, and then we can work with it. So, it's just how we specify things. But really, when you create this function, you say, does my function only work with dogs, or does it work with any base level class of whatever dog inherits from, which is animal? And you say, no, well, my function works with all kinds of animals. Okay, why limit it to dogs? Don't limit it to dogs, limit it to animal, right? And now you can use any animal that you want to pass, and it'll go there. Boop. Right? And the cool thing is that even if this was dog, right? So here I have created a dog instance, and I have assigned it to a variable which holds dog instances. This is an animal, and this is a dog. But C++ says it's okay to treat a dog as an animal, right? Because we made it public. Which means that when I do this, this dog will be converted to an animal right here. And now it's being treated as an animal, right? So let's say I change this to my dog, and this is my dog. So it's less confusing with just proper naming. So now this my dog, which is a dog, right? It's a dog. When I go here, it turns to an animal. We'll talk about so it was asked, do all the access modifiers work for inheritance? We'll talk about what happens to access modifiers when we deal with polymorphism in a little bit, right? We'll talk about that. But for now, hold on to that thought. But here, the only thing I want to say is that C++ can convert a derived instance. So in this case, the derived instance is here, to a base instance, right? We can go from a much more specific idea to a much more general idea, right? Okay, so let's keep going, and more things will clear up. Now, and this is kind of why it's called polymorphism, right? It has taken different forms. This is one of the reasons why it's called polymorphism. We'll talk about a few other things that will give us more insight as to where this many forms come in. Now, we can also do this with pointers, right? So here's pointers. So instead of an actual regular variable, we have a pointer of type animal, and we call it my animal. And then I say my animal equals a new dog, right? Same thing. And then I can delete it. And then I can say my animal, it's a new cat. And then I can delete it. And then my animal, it's a new giraffe. And I can delete it, right? So it doesn't matter. You can also do this with pointers. It's perfectly fine. In fact, well, I won't spoil it, but pointers are more important to polymorphism, and we'll see why in a later slide. And this is one of the reasons why once you start dealing with object-oriented programming, you kind of really have to go to pointers. We cannot stay using these. This has some limitations. We'll talk about those in a minute, but these limitations that this have doesn't let us work with polymorphism and inheritance very well. But what does let us do all the nice things about inheritance and polymorphism is pointers. We'll talk about it why, but we can do this with pointers, of course.
Now, you say, okay, well, okay, I can see, as I think someone said that was pretty cool, right? Okay, so yeah, it's cool. You're like, okay, great. I learned something new. Can I live without it? It seems like I can, because I can just, whatever, I just make this a dog. And this is a dog anyways. And if I want to do it for a cat, then I copy paste and I make another function and do it for cats. And it's like, all right, you can live with that. But see, there is more power to polymorphism that comes once we start to mess with a bunch of data. So for example, imagine that you have a zoo, and in that zoo there are 4 dogs, 2 cats, and 1 giraffe. Now I know that in zoos, for the most part, you have other exotic animals, but we have a dog class, so let's use dogs. We have a cat class, so let's use cats. And I threw a giraffe to actually make it look into a zoo, right? So we have 4 dogs, 2 cats, and 1 giraffe. How would you code this? How would you put this in your code? Well, one way is you could do this into arrays, right? So you can have an array of 4 dogs, an array of 2 cats, and maybe you don't have an array for the giraffe, because the giraffe, it's on its own, right? But if we make this into an actual zoo, maybe you have 5 dogs, 10 cats, 10 giraffes, 5 elephants, 30 monkeys, 10 apes, 50 birds, 30 crocodiles, whatever, right? So in actual zoo, you will have tons of these animals. So the way to go about it would be to use arrays, right? You would have an array per different species, or for different species. So one way to do that is to do the following. We'll have an array of 4 dogs, right? And the first dog is a 3-year-old 10-pound Chihuahua. And then the next dog would be a 2-year-old 45-pound Labrador, a 10-year-old 15-pound Chihuahua, and an 8-year-old 55-pound Greyhound, right? So we have an array of 4 dogs. And then we have an array of 2 cats. The first cat is a 1-year-old 8-pound cat, and the next cat is going to be a 5-year-old 20-pound cat. And then we make our giraffe. Our giraffe is a 9-year-old 450-pound giraffe. I don't know what the average weight of a giraffe is, so if I'm way off, don't make fun of me. But it says, let's just say that it's 450-pound giraffe, which is 9 years old, right? Okay, you're able to achieve this, right? And then imagine, what would you do if this was tons of different animals, right? So you just have a bunch of these, right? A bunch of these for the different types of animals. But then, what if we wanted to start doing things with these animals? So we want to feed them. We want them to eat, right? Because that's what we do. That's what the people that work at the zoo, that's what a lot of them do. They feed the animals. So what if they wanted all the animals at the zoo to start eating? Well, for the dogs, they will have an array, right? And in this array, they will have, okay, from 0 to 4, let's call the eat function in the dog's object, and we feed it 5 pounds. I just pick 5, arbitrary number, right? And you will do this for all 4 dogs. So all these 4 dogs will be given 5 pounds to eat, right? All of the 4. And then you go and you do it again for cats, right? So now from 0 to 2, you also feed them 5 pounds each. And then you go to the giraffe and you also feed it 5 pounds. Again, how much they should eat, for, I know giraffes eat more than dogs and whatever, but here let's just say we're feeding 5 pounds of food to each animal equally, right? So the point here is that you would have a bunch of loops. And if you had, again, hundreds of different kinds of animals with many arrays, you would have a bunch of for loops to start feeding every single one of those animals, okay? Now, then I propose, why don't we use polymorphism? What do I mean? Well, all of these 4, these 2, and this giraffe, all 7 of them are animals, right? They're all animals, which means I can put them all together in one single array. And my array, instead of having an array of dogs, an array of cats, an array of giraffes, I have an array of animals, the much more generic version of them. And I call this zoo animals, right? And I have 7 of them. The first 4 are dogs, which is the 4 dogs that I have here. The next 2 are the cats, which are the 2 cats that I have here. And then the last one is the giraffe, which is the giraffe that I've created. All 7 of them are now in one single array. And if I want them all to eat, well, now I can just do one loop. So I went from 3 loops, well, actually 2 loops and a single variable usage, to 1 loop. And in this 1 loop, I have fed all zoo animals 5 pounds. And if you had, again, hundreds of different species and hundreds of different animals, you can have one huge array, only one, and with one loop, you would have them all eat 5 pounds. This saves you tons of code, right? You have coded way less by doing polymorphism because everything is taken into account that the fact that they're all animals and you don't have to worry about it. Another mentality, since we keep using animals, well, I keep using animals. I shouldn't blame you for that, but I keep using animals. Think of a farm, right? And then you have the person that goes and feeds the farm animals, right? What's going to happen is that farmer will go out and it'll say, okay, horses, eat something, right? And then he'll go and say, ducks, eat something. And then he'll go and say, pigs, eat something. And donkeys, eat something. And dogs, eat something. And roosters, and chickens, and donkeys, and sheep. That takes too long, right? What if instead of saying each one at a time, you just said, animals, eat something? That's it. You're done, right? So I know it's not as easy as that when you actually have a farm, right? It's not just saying eat and they get to eat. But my point here is that when you start to describe these things, you can go and describe each species, each specific type, and specify what they want to do. But if all the specific types are going to do what a generic type would do, we just put them all together and say, hey, all of you do that, and you're done with it. So here, the eating function, it's applied to every single animal, regardless of whether it is a dog, cat, or giraffe, right? And we can show that real quick here. We can just come here. Let's delete this amazing function that we did. And then I can just say something like, okay, well, I have a variety of animals. Let's say I have 5 of them. Let's say pets, right? Let's say we have pets. We have 5 pets because that's you say we want to have 5 pets, and let's say we have 2 dogs, and we're just going to use the default constructor so we don't have to type much, right? So we have 3 dogs, and then we have a cat, and we don't have a default constructor for cat. Let's say we have a 1-year-old cat of 10 pounds, and then another cat of 2 years old of 15 pounds, right? So now here I have created my pets, right? I have my 5 pets, and they're all together in a single array rather than in one array for dogs and one array for cats, right? So the power of polymorphism is that we can apply this to collections, to arrays, and of course you have heard of lists and vectors and these kinds of things from other classes. We haven't talked about those here, but as you can imagine, this mentality will also apply to them. And the first time I found out about this, man, I was like, man, whoever did this is a genius, because this has saved me to write so much code like you can't imagine. This is very powerful, okay? All animals are eating with much less code. There's a problem with using a derived instance in a base type variable. If my dog is treated as an animal, like right here, so this dog is treated as an animal, how would we know it can bark? And it's the same problem that I gave you earlier. If I tell you, can you take care of my animal? What if you have a rule? I will take care of any animal except those that can bark. And I say, hey, can you take care of my animal? Well, you have a problem. You don't know if the thing I'm offering is a dog, right? So in here, how do we know that this thing, this my dog, which it is a dog, right? There it is. It's a dog. How do we know that it can bark if we're treating it as an animal? And we know that animals in general do not bark. Well, we can't. That's one of the downsides of doing these kind of things. So if I treat a dog like an animal, I can use the animal functionalities, but I cannot use the dog functionalities, right? So let's just go back and say, okay, we have dog, my dog, this is a dog. Again, we'll go with a default dog, and then I can say my dog that bark. Let's just say, right? So I have all the public members of animal and the public members of dog. And let's say I want to bark, right? And then I can also say get age, right? Or get weight. But now if I treat this like an animal, this is fine, because an animal has the get weight function. But an animal does not have the bark function. So my dog that bark, it's gone. I cannot use bark, right? So it's like, hey, I don't know what you're doing. I really don't know what you're doing. Oh, not eat, bark. I say bark. All right, so here, the animal, the class animal doesn't have a bark function. And you might say, well, but it is a dog. I'm like, yeah, it is, but we said we're going to treat it like an animal, therefore you don't have the ability to bark, or this thing doesn't have the ability to bark. If it's private, so if it's private, the dog is just a dog. If this is private, right? So forget about this right now, right? Forget about this. If this is private, like it is right there, or if I actually type the words private, if this is private, dogs can only be put in dog variables, right? So I can only do something like dog, some dog, dog. When it is private, when this is private, I can only put a dog in a dog variable, nothing else, all right? When it's public, I can put a dog in the base class type variable. So I can put a dog in an animal variable. I can put a dog in an animal variable. All right. That's it. That is all this thing is saying, is that when you put a value of an instance of a dog, you of course have the ability to put it in a dog variable, right? Of course, that's obvious. That's given with the whole idea of classes and objects. That's this. But now that we have inherited from animal, we have a relationship. The relationship is a relationship, which means a dog is an animal, which means I should be able to put dogs in places where I put animals. Why? Because dogs are animals. So but because we have control, right? We're the programmers. We should have control of everything, right? So even though that a dog is an animal, I should have control to say, okay, treat it like an animal or don't, right? It should not be forced upon us. We should be able to have that choice to be able to choose whether we want to have this feature or not. So we have the ability to specify that. And when we make it public, we're saying, well, it makes sense that because a dog is an animal, I should be able to put a dog instance in an animal variable. That's all it's saying. Now what follows up from that is, what I am saying now is there is a problem because of that. And the problem is that when I treat a dog instance as an animal, when this is a dog, however, publicly speaking to everyone is an animal because this is specified by its data type, I only have access to the things that animals have: eat, get age, get weight. I don't have get breed, I don't have bark, because this is treated as an animal, right? So I only have these three. However, my some dog can't, well, just give me an error. So let's say, let me just put a semicolon here. Now, some dog has everything, has the animal stuff, get age, get breed, get weight, and no, get weight, get age, and eat. And you also have the bark and the get breed, these two. Right? And the reason for that is because this is being treated as a dog, as it should be, right? Because a dog is a dog. However, because we want to be able to use polymorphism to use specific objects as general objects, we have to pay the price for that benefit. And the price to that benefit is that when we treat a specific object as a general object, we only get the general functionality. We lose the specific functionality, even though it's one of those things, right? This animal that I have stored in my dog, it is a dog, but you know, I lost it. I lost that extra functionality that came with dog by having this thing right here. So that's the downside. That is the thing that we lose when we're placing a value of a derived object into a base type variable. Okay. So there is a downside, but there is a way to as we introduce more of these concepts of computer science and object-oriented programming, you realize that we speak about the theory, we talk about how we code it, and then once we have the code, we're like, okay, well, that gave us some issues. Okay, how do we overcome those issues? So now the question, and I'm going to leave this for you to just kind of think about in your head, is how do we overcome this problem? The problem that I have treated a dog as an animal and I lost the dog functionalities, right? So we'll talk about that on Monday. So we'll continue the polymorphism lecture on Monday. Once we say that a dog should be treated as an animal, well, we lose the stuff that we know about a dog is. So for example, here's an example. So treating a derived instance as a base instance only gives us access to the base instance public members, right? So the animal class, we could declare a variable of type animal and we put a dog instance in it. And then I say, my dog eats. Well, that's perfectly fine, right? Because if I go back to our code, our animal class had an eating function, which was public, right? All right, here we go, eat. So I can eat from an animal, right? Here we go, eat 3 pounds. But then I can say, well, what if, can it bark? And that the thing is, it cannot. It's an X. Why? Because animal doesn't have a bark function, right? None of these is a bark function. So because animal doesn't have a bark function, when my dog, which is a dog, is treated as an animal, the only access that I have is the animal stuff, right? Because it's been treated as an animal. You cannot treat something as an animal and then use members of another class. It doesn't make sense. So we can no longer use the function bark despite this thing being a dog, right? So that's a problem. Now, so you might say, okay, well, if I took a dog and I made the dog treated as an animal, can I take the animal, which is a dog, and treat it back as a dog, right? So if I say, hey, can you take care of my animal? And then before I hand it to you, I say, hey, it's a dog, right? Can I get that idea back from it being an animal back to a dog? And the answer to that is no and yes. It is no with regular variables, right? So here, a dog instance is put in an animal variable, like we did earlier. And then I create a dog variable, and then I try to put this animal into the dog variable, right? And this is a problem. Why? Because an animal is not a dog, right? An animal is not a dog. A dog is an animal, but an animal is not a dog. It could be a dog. It could be, but it is not a dog. We don't know that. It could be anything else. It could be a giraffe, a cat, something else, right? So we cannot make the assumption that an animal is a dog. We can very well make the assumption, because we know it is, that a dog is an animal, but the reverse is not true, right? The reverse is not true. So we can go from a dog to an animal. We cannot go from an animal to a dog because we don't know. We just simply don't know. You know, you the person know, I know, right? Because it's my pet, I know. But the computer is like, I can't make that assumption. What if this was originally an animal or a cat, and then you try to put a cat into a dog variable? How will it know that this is correct or wrong, right? It wouldn't know until you start running your code, and that would probably make it crash or do all sorts of weird, funky stuff. So the problem here is that you cannot do this, right? And it actually makes sense within the context of variables, right? So if I have, let's say, if I have a, let's just pick red. So if I, in here, let's say this is the animal object, right? This is the animal object. And then I come here and then let me grab green, and then I extend it, right? So we said that the way we can look at a derived class is that the derived class is an extension of the base class, right? So let's say that the derived class comes here and extends it a little bit, and then you know, because the derived class is the base class too, then it kind of does something like that, right? So let's say that this is dog. Oops, this is dog, and then we have animal over here, right? And so dog is both. It's the green and the red. And animal, it's only the red, right? So now, what happens here is that you're putting a dog into an animal, right? And if you remember, this is in memory. If you look at memory, an animal will occupy so much memory based on how many members it has and whatnot, right? A dog is everything that an animal is plus something else. So that means that the derived classes occupy more space than the base classes, right? So, and if you look at this, you can see that an animal only occupies this amount of space. A dog occupies all of this space. So the derived instances always occupy more space than the base instances. So what is going on here is that if you put a dog instance into an animal variable, means you're putting something that's bigger in a place that it is smaller. So in order for that to work, you have to get rid of the excess. You have to get rid of the extra stuff. So what happens is that dog, when putting into an animal, you lose the dog part of it. You lose the dogginess of the object. You lose the derived part of the object. meaning you lose kind of this. The moment that you put it into an animal variable, you lose it because you don't have space in memory to put it. You only have enough space for an animal, which is the red part. And this should remind you kind of data demotion, right? If I have 3.14 and I try to put this into an integer, what happens to the x's? The x's goes away. So same thing here. I'm trying to put something that's bigger in something that is smaller, but it's fine because they're the same, right? A dog is an animal, so I can do that. However, an animal is smaller than a dog, the idea at least. Therefore, whatever extra dog brings into the table has to be deleted, right? So that's what happens with normal variables. With normal variables, we lose it. We lose our dog functions that came with it. However, that doesn't happen with pointers, and there's a good reason for that. So so let's talk about, from now on, for us to be able to properly use polymorphism, we have to go with pointers. And that, like, you might say, man, I didn't want to do pointers. We have to do pointers to do polymorphism. Otherwise, again, we lose the derivation part of it. And if we lose it, then we just lose inheritance altogether, right? If I'm going to treat a dog as an animal and it's going to become an animal, then why did I do inheritance, right? I just lose it. I lose everything that was about a dog. So it becomes pointless. So we have to actually we want to use it because it's useful and it's powerful. So we have to go to pointers. Pointers is the only way. So a dog pointer can be treated as an animal pointer, right? Same analogy. Why? Because a dog pointer is an animal pointer, right? It just makes sense, right? If you point to a dog with your finger, you're also pointing to an animal, right? Like if you see an animal on the street and you point at it with your finger, think of it as that pointing with your finger. That's a pointer, right? Well, you're pointing to a dog, but you're also pointing to an animal. So a pointer to a dog is also a pointer to an animal. It just, makes sense. And of course, we have the same issue. We can only access the public members of the class animal. So we can eat, but we cannot bark. So you might say, okay, so far, everything is the same. Now, before we move on to the next slide, let's contrast this thing that we did up here with pointers. So let's say that I have, the dog. We have the animal, right? And then I come here, let me get green, and then we have the dog, which extends it, and then dog is everything that animal is too, and this is dog, right? And then you have a pointer. Let's just make it blue, right? Yeah, the blue. So you have a pointer here. Let's say this pointer. You have a pointer in memory, and this pointer will point at the dog, right? And then you say, well, you know what? I no longer want to point to the dog. Let's say you want to have another pointer, and this pointer will point at the animal part, right? It doesn't matter what the pointer points to. It doesn't affect the object itself. When I created the dog in memory, the dog occupied all the memory that it needed to occupy, which was all the green. That includes the red, of course. So all the green with the red, all of that gets put in memory. And it doesn't get deleted, right? Because we created with the new keyword. It only gets deleted when you delete it. When you, the person, the programmer, wants to delete dog, that's when it's gone, right? So now in memory, you have two addresses, kind of. You can think of two addresses. You have the address of the dog part, which is the whole thing. And then you have the address of the animal part, which is which is only the red thing, right? Which, a spoiler, it's the same, right? If we recall back to our memory class, it was a table, right? And in our table, what we said was that the first byte that the value occupies in memory, that's their address. So imagine that. Let me get red again. Imagine that animal occupies this amount of space, right? And then you get the dog, and the dog occupies, again, because the dog overlaps, occupies this amount of space. Well, both the address of the animal is here, right in the beginning. And the address of, let me get blue. The address of animal is right here, right in the beginning. And the address of dog is also where? Right here, also in the beginning, right? So basically, what happens is that if you treat the pointer, the dog pointer, as an animal pointer, you're still in the same place. It's the exact same spot, the very beginning of memory, right? You don't lose anything. And you only have access to the public members, meaning you only know that you go this far. You go you only use this red square. However, if you treat it as a dog pointer, you get the whole thing. You go from green to green. You get the dog part and you get the animal part and the dog part. That's why with pointers, this is perfectly okay, because the memory and the variable are two separate things. You have memory in one place that holds your dog instance, and then you just simply use the pointing part as to know what part of the object you want to point to. Do you want to point to the base instance? You want to point to the derive instance? It doesn't affect the object itself, right? So this is why pointers, it's okay for us to use polymorphism, right? So now you might say, well, okay, so we created a dog instance and then we get an address to it, right, with the new keyword. And then we saved it into an animal pointer, meaning we're treating a dog pointer as an animal pointer. Now the question comes, can I reverse this? Can I go from an animal pointer back to a dog pointer? And the answer is yes. So we can do that with pointer. And to do that, we do something called typecasting. So because the full object is stored in memory and we can only have a pointer, we can change to how we treat it, right? So to do so, we use the typecasting functionality, right? So here I have a animal pointer, and in it I put a pointer to a dog instance, right? And now I say I want to treat this animal as a dog again. I want to treat it back as its original thing. All I have to do is in front of the variable, in parentheses, I put the type that I want this value to be treated as. So this is a animal pointer. I say I want to treat it as a dog pointer. And so basically this says, hey, treat my animal like a dog pointer. It's the reverse, right? So we're telling C++, whatever value is in here, whatever value this is, treat it as a dog pointer. That's what typecasting is. Treat it as this thing right here. So let's just do an example. So let's delete these, right? Let's delete all of this. So let's just say I have an animal pointer. It's going to be my dog. Well, let's just say some animal, right? And this is going to be a new dog, not a new dog. And this dog is going to be, we need a breed. So it's going to be a, let's say a Labrador, which has a weight of 50 pounds, right? It's bigger. All right, so we have created a new dog that is a Labrador with 50 pounds, and it has an age of 0 because that's the default based on our dog class. Here you go. It defaults to 0, right, for the age. So then what I do from this is that I would like to then treat these back to a dog, right? Because right now, if I do some animal and I look at its functions, I get eat, get age, and get weight, which is the only animal functions that there is, right? I have eat, get age, get weight. But I don't have the barking function or the get breed, and I want those, right? So then what I do is that I would like to treat some animal back again. I want to treat it back to a dog. So what I can do is well, let's create a new variable of a dog pointer. In this dog pointer, we're going to call it some dog now, right? And in here, what I've said is that if we try to do this, this will not work because this is saying, hey, I would like to create a dog pointer out of an animal pointer. And it's like, I don't know how, we cannot just by default treat an animal like a dog, right? Because we don't know that an animal is a dog, right? So what we do is that we actually specify to C++, we say, I want you to treat it like a dog, right? Because you have control of the language. So to do that, to say, no, treat it like a dog, right here in the front, in parentheses, you type what you want this to be treated as, right? So this says, hey, treat the pointer, which is an animal pointer, now treat it as a dog pointer. And when I try to do this, some dog, then I now have the functions that I needed, right? So now I have the get breed and the bark. Okay, so we can go back. So let me just put it again. So I can do animal pointer, copy of animal, right? I can put some animal, right? I can put an animal pointer into an animal pointer. That's obvious. But I could also do some dog, right? Because a dog pointer is an animal pointer, right? So I can convert whatever a dog pointer is to an animal pointer. That's obvious. We can do that because the dogs are animals. The reverse, however, it's not. So if I was to do now again dog copy of dog, right? And I want to put this one in here, I have to cast it. I have to say, hey, this is a dog pointer, right? So kind of in summary is that when you go from a derived version to a base version, you can simply do it, no problem. When you go from a base version to a derived version, you have to tell it, you have to tell C++ that it has to do that because it doesn't know. And again, this is the analogy of, hey, take care of my animal, right? Until I tell you actually it's a dog, then you know that it is a dog. So in here, the compiler, C++, is that friend who doesn't know what animal is until it is told that it is a dog. So here I'm telling it, hey, it's a dog. Treat it like a dog, right? And so this is how we are able to reverse it. And it should be quite obvious why we can go from derived to base, right? Because the base is a generic version of the derived version, right? But you can create many derivations from the base class, right? A base class can be inherited from by a variety of objects. And because that's a thing, you don't know which version should it be more specific to. You don't know the base instance, how should it be treated as a much more specific object? Should it be a dog, a cat, a giraffe? It doesn't know that. It only knows that it is an animal. And you, the programmer, you're the only one who knows that because you programmed this. You're the one who's writing the software. So you have to tell it, hey, this is a dog. Treat it back like a dog once again, right? So this is how you can go back and be able to start using the dog functionalities. Now, for the most part, this is not 100%, but for the most part, is that if you do something like what we have here, if we do something like this, right? If we create a dog and we store it into an animal, why would we do that, right? Like, why would we do that? Generally speaking, if you know that you're making a dog, you make it into a dog variable, right? Why would you go into an animal variable? The times we do that is because we don't care about the specifics. So for the most part, I can say that most of the time, we don't cast back. We don't do this, okay? We do that sometimes. I would say many times. But if you were to put all the programming that you're going to do, most of the time, you don't do the cast back. And the reason for that is there's a reason why you treated this as an animal in the first place, all right? You didn't care about the specificness of this instance. You only care about the genericness of that instance. So if you care only about the genericness of that instance, you shouldn't need to go back and treat it as a much more specific version of itself. However, I'm not saying that you should never do that. I certainly do that sometimes, and we sometimes have to do that. But if you look at assignment 6, I treat the shapes that you're making, I treat them like a shape class. I don't have to turn them back into square, triangle, or whatever, right? If you haven't done the assignment, you'll see what I mean once you start looking at it. But the point here is that I don't have to, right? I plan to treat your classes that you derive from my shape class as a shape. And I have no intention whatsoever to convert them back to the type that you have created, right? And so basically what I'm saying is, most of the time is if you do the top thing, there's a good reason for it. And that is that you don't care about the specificness of it. But of course, you have the option because sometimes you have to. Sometimes you have to go back to the specific part of this object to be able to do the things you want to do, okay? The concept is very easy. To go from a derived instance to a base instance, just simply set it equal to each other. No issue. To go from a base instance to a derived instance, you have to cast it manually. You have to say, this is that, and then it does it. Okay, here we go. So here's how typecasting works, sort of as a formula. If you want to see it as a formula, maybe you like math. If you want to see it as a formula, this is kind of how it works. So typecasting is used to treat one data type as another. So basically, what you typed. So the question is, if the casting to a dog pointer of my animal, basically this thing right here, this thing in blue right here, is going back to specifics. This is saying treat this generic animal as a dog, and we're talking about pointers. So treat this generic animal pointer as a dog pointer, right? So what I'm saying is the only time, for the most part, when you use casting is when you go from a base instance to a derived instance, and the derivation is the specific one. The base is the generic one. And so this is why you need to do that. And again, just think about the reasons behind it. A dog is an animal. You don't need to cast that. That's obvious, that's known. However, an animal is not a dog. It could be, right? It could be a dog, but generally it's not. We don't know what it is. But you, the programmer, know. So what I'm saying is this animal, you know it's a dog because you created it, right? Right here. You have created the dog. Therefore, you're saying, treat it like a dog again. Once again, go back and treat it like a dog. So this is me treating it like a dog right here. And I save it, right, into my dog pointer variable. So then I can use its members. Does that make sense? It's just how we treat data. We're not changing the data. Behind the scenes, in memory, the dog is living its life with it. The dog doesn't even know you're struggling to understand pointers. The dog is like, they're just hopping around in memory, chilling, eating, barking, whatever. The dog doesn't change. The data itself behind the scenes in memory, it has not changed at all. It's a dog instance just sitting in memory. It's how you treat that chunk of memory. You can choose to treat that chunk of memory, which represents a dog, as an animal, or you can treat it as a dog. It's up to you, right? However, you might need to change it. You might need to say, well, sometimes I want to treat it like an animal. Sometimes I want to treat it like a dog. So to do that sometimes and to switch it from one to the other, you either have to go from a derived to a base by simply setting them equal to, or you go from a base to a derived by casting it, by saying this is that. And that's it. That's it. It's just how we look at things. It's all the only thing that is changing, how we look at an object, right? So this is the formula. So a typecasting is used to treat one data type as another, right? It doesn't only apply to objects. It applies to any data type. Any data type that we have in memory or that we have available, it applies to all of them. Ints, floats, booleans, what else? Enumerations, other objects. It applies to everything. It's a data type, right? We can use that to treat a base, but of course, the specific use is that we want to treat it. We want to treat the base pointer as a derived pointer, right? So the format to that is we say, okay, here's the data type that we would like to store our value as, which is going to be a pointer to a t, right? A t is the base of the class, the base class. And I say I want to convert it to a pointer to a t, the base class. The p is the pointer value of the base class, right? So p is the pointer value of the base class. And then lastly, p sub t is the pointer to the derived class, right? So it's just this in a formula way. If you like formulas, here's the formula of how you can look at a casting, right? Derived pointer, the variable, which will hold that pointer value, that equals to the pointer being casted as a derived type pointer. Okay, so here it's the same thing, example, formula. Okay, so things doesn't stop there. Things get more complicated, but that's good because we get more tools and more flexibility to write interesting software. So you can only treat a dog instance as a dog instance, right? So this is what we just did. This thing we did makes sense, right? A dog was put into an animal, therefore I should be able to treat that animal back like a dog, right? I'm just doing the reverse. Here's an interesting problem. Here is a new animal, not a new dog, a new animal, right? And this animal gets stored in my animal variable, pointer. And then I try to convert this animal into a dog. This is a no, there's a problem, right? So let's just look at that. What I'm saying here is that we simply were able to treat a dog as an animal, and then we did the reverse. Treat back the animal as a dog, right? Easy peasy. Now, what I'm changing this is now make this an animal, right? An animal occupies an age, let's say a 10-year-old animal with 50 pounds, right? And so now what I'm saying is this is problematic, right? And you should look at this code and say that's wrong, because an animal is being converted to a dog, but this was not a dog, right? This right here, this was not a dog to begin with. And now I'm saying treat it like a dog. That's a problem, because you did not create, let me go back to the dog class. You did not create this piece right here. When you did new animal, you only created the animal part, this, but the dog part is missing, right? That was not created when you did this. Now I'm saying get this incomplete dog, which is only an animal, and treat it like a dog. That's bad. Now, C++ lets us do that because, again, we have control of it. We are the programmers. We can say what to do, whatever we want, right? So here I'm saying treat this thing as a dog pointer. And even though it seems like there are no errors, and we'll talk about what kind of errors we get. This, you might say like, oh, there's nothing wrong. You know, it ran, it had no crashes. This is perfect code. This is not right. And let's talk about what exactly is wrong with that. But let's just talk about another example that you might see why it's even more problematic. If we cannot convert a, yeah, so if I try, let's just try it. So if I try to do some dog bark, right, that might be problematic. It might not be though, and there's a reason why not. So if you expected an error here, you are right. This is an error, but there's a reason why it didn't crash. Okay, we'll talk about it in a minute. But there's a reason why it didn't crash. So what's even worse is we're trying to treat something. So we try to treat a generic version as a base version, like a truly generic version, an animal. We try to treat it as a dog. We don't get that stuff. Okay. What's even worse than this, because this you might like try to justify it. You might sit there and be like, I don't know, man, like I should be able to do this. You might try to justify this. But what's even worse is if you try to convert something that it really is not, like absolutely is not, to that other class. So here is a cat pointer, right? And I create a new cat, and then I convert the cat to a dog. This is problematic, right? A cat is not a dog. You can make the case that some animals are dogs, but certainly a cat is not a dog. So this is even problematic. You know, you're like, what are you doing? You know, you're doing this. This is wrong. Okay. But C++ lets you do it. And obviously what we saw right now is that nothing crashed, right? And like we were hoping that this will make it crash, as Rolf mentioned, but it didn't. And there's a reason for that. One is, I would say the reason is we got lucky. When you're writing software, don't expect to get lucky, okay? But let's say why, what happens? So what happens when you do an incorrect cast? So here's an example of incorrect cast. You cast an incomplete base instance to a specific instance, so a derived instance, right? This is problematic because you're missing the specificness on this, right? The other one is when you cast something that it's not even the same to the other thing, right? So I'm trying to cast a cat into a dog. That's an incorrect cast. And look, man, this you have complete controls. That's why C++ sometimes is scary. But what I'm saying here is that, you know, you can do some funky stuff with this. I could say, you know, a float pointer. Let's just say a number. And this is going to be a new float that has 3.1416 like pi, right? And then I can say treat this number. So let's just say a weird dog. Treat this as a dog, right? Does that make sense? It doesn't make sense. It doesn't make sense at all whatsoever. You're treating a floating number, which is at 3.1416, as a dog, right here, right? That's like, what are you doing? Like, what exactly are you doing when you do this? And we could try. Maybe this one does crash it. Let's see. Let's just say get breed, right? They didn't crash it. It didn't crash it. There are reasons why it didn't crash it, but as you can see, this doesn't make any sense, right? We don't even know what the breed would be. Let's just say see out get breed. Okay, well, yeah, okay. Let's just say let's do get H then. Let's just see what happens. Look at that H. Have you ever seen a dog that old? So I do this not to confuse you. I want you to know that there is a problem here. There's a big issue, right? is that we have complete control of what happens behind the scenes. I converted a floating number into a dog. That makes no sense. And how do you know it makes no sense? Because you look at the output, 1078. That's what is that? That's how old the egg. Let's do the weight. Get weight. Let's just, since we're having fun with this. That's a very light dog, right? So my point here is that when you do these kinds of conversions, there's a problem. And what kind of problem we get, it's based on what I have on this slide. So when you do an incorrect cast, when you cast something that it's not into something that it's not, let's just say, you have one of two problems. You would have the problem of when you do not initialize a variable, right? So remember, when you don't initialize a variable, what happens? You get garbage. You get some random value in it, right? We showed this when we started to do the construction of variables, right? If we don't initialize them in the colon method and we try to show what's in them, you get some strange number, right? It's what we just got. We got it. This is actually the error that we got. We got garbage, right? The second problem that you might get is the problem that you get with arrays, right? So if I have, let's just show it. If I have an array, let's just do it down here. If I have an array, let's say we have an integer array of 10 values, right? And we set them all to 0. And then I go cout array 50, right? Hopefully it gives us the error. Okay, it didn't give us the error again. And there's a reason why we're not getting that error, but let's just go with something crazy like 50,000. Maybe that'll force it. Let's see. Let me comment this out so we don't have prints. There you go. Okay, so with 50,000 it did it. With 50, and this, look, leave this as an exercise for you. I'm gonna leave that as to you. Why is it that when I put 50, oops, hold on, what did I click? Okay, why is it that when I do 50, it doesn't crash? We didn't crash the program, right? We only have 10 values, but I'm going to the 50th spot. I'm going out of bounds, but it didn't crash the program. But if I make this into like 50,000, let's just say, this did it, right? It crashed the program. So this is why also the bark function didn't crash. This is why also the get weight didn't crash. It's for the same reason, right? Man, I'll just tell you. And it's because we get lucky, all right? Your program has a fixed amount of memory in RAM that you can use, that it's given access to. When I give 50, I happen to be still within that limit of memory that was assigned by the operating system to your program. So you get lucky and pick a value that's still within your, let's just say, within the realm of memory that you have available, right? You have a fixed number of memory that is allowed and allocated for your program. When you do 50, my claim is that you're lucky to land within that allocation space, right? When I do 50,000, I'm trying to overshoot it, like on purpose, so you can see. Is you're going out of that set of memory that was given to you. Now you have a problem. You went to memory that's not yours to use, right? It's like you went into your neighbor's yard. Think about it that way, right? So now you went into your neighbor's yard. You went into another program's memory. You went into the operating system's memory, and they tell you, hey, you can't do that. Get out of my yard, right? So that's what this is: access violation, reading location. That is, get out of my yard, man. This is not your property, kind of thing, right? Fortunately, the program doesn't have a shotgun, so we don't have to worry about it. What was the uninitialized variable you mentioned? Oh, remember when we don't. Remember when we do it here, when we construct an animal, right? This is how we initialize them, right? If I don't initialize age, like I just leave it like that, right? And then I show it. What value would age be? It's unknown. We don't know what value age would be because we haven't given a value, right? So if I print this, you would get some random value that whatever number happens to be there in memory, that's the value that you get. So this is all I'm saying, is that when you don't initialize a variable and you just declare it, like you create the variable but you don't give it a value, it just gets garbage. It has a garbage value in it. And so what I'm saying is that when you do casting, like the casting that we did here, we casted a float into a dog, absolutely nonsense. Well, what happens is that here we have two problems. We either have the problem that we have garbage as part of our object, or second, we went out of bounds and we're going to crash the program, which I show with the array example. Okay, so don't do bad casting. And so there are ways to have a safer casting form. There are other casts that have been added to C++. This is the old type of cast. This is the C cast, back the very first type of cast there was. This is this one. Then they created a few other casts to make it safer, so that if you try to do something odd, to not let you do that, or to try and give you a much more representative error instead of just telling you, hey, out of memory, I don't know, you got an error, right? So that they have created other casts to do that. We won't talk about those today. We can talk about those some other time. But what I want you to know is, as we're talking about polymorphism, is we're not talking about like C++ casting methods, although they're important for us to do this properly. What I want you to know is that once we go from derived to base, we can go back from base to derived by doing a casting. And the casting is manual. You have to do it. C++ doesn't do it for you, okay? That's the whole thing behind casting, okay? Later, we will learn of other types of cast. If we have time, we can include it in the later lectures, but there are a few other casts. If not, I'll let you look those up. But this is the harder type of cast because you have complete freedom, right? So if you understand this cast, going to the other ones should be much easier, right? And some of you have used for some of the assignments. You've used static cast, you've used dynamic cast. There's a few other casts. We won't touch them for now, okay? Any questions about casting? Right. Again, the concept, programmatically speaking, is very simple, but we talk about it so much because we need to understand it. We need to understand why we need it, why we use it, okay? Base to derived, you cannot make an assumption about its much more specificness. You have to tell the computer what it is. From derived to base, no problem. It's easy to remove, but it's not easy to add, right? You can remove the excess, that's not a problem. But to add the specificness, that's complicated. It requires thinking, and then it requires work. So that's why you have to do it. Okay. All right, let's talk about one more thing, which is related to polymorphism. All right, so here we have, with inheritance, we were able to describe a dog as follows, right? So we created two different classes. We created, and let me change the color since we use red for a lot. So we created the animal idea, and then we create a class out of that animal idea, characteristics and functionalities. And then we created the dog class. And the dog class says, hey, everything that animal is, that's also me, but with some much more specificness. I'm a little bit more specific than animal, right? Which means give me all those members, all those characteristics and functionalities, and then on top of that, add this extra functionality. And this together, these two together, that's a dog, all right? So we learned that with inheritance. Now the problem is, here's where it starts to even get more fancy with polymorphism. The problem here is that we know that all animals eat. Okay, if you're a hardcore biologist, maybe you know of an animal that doesn't eat. Maybe they get energy some other way. But we have been talking about 10 different animals, right? Cat, dog, lion, bunny, all those 10. To us, those are the only 10 animals that exist for this exercise, okay? So we know that those 10 animals, they all eat, okay? But they don't eat the same way, okay? A mouse doesn't eat the same way that a dog eats. A giraffe doesn't eat the same way that a elephant eats. The elephant uses the I forgot what it's called, the thing to grab stuff and then eat it. The giraffe is very tall, it eats from the trees, so on, okay? So not every animal eats. However, every animal eats, however, not every animal eats the same way. So there is a problem, right? So you're like, okay, well, our animal class says that we have an eating functionality, but our specificness, all these specific classes, they all do it different. Right? There's a problem. So we would like to be more specific on how a dog eats, right? We want to specify how this dog eats. Right now, we cannot do that. The eating function belongs to the parent. It belongs to the base. But dog says, I would like to add logic to this eating function. I would like to make it more specific, right? I am, as an object, I am more specific, but I want to make a particular function even more specific, okay? The function itself, I want to make it more specific. So now we introduce a new thing called a virtual function. So we can state in the base class, in our case, we're using animal. So in the animal class, we can state that a function can be modified by its children, by its derived classes. In our case, dog, cat, giraffe, etc. How we can do that? We call a function, we declare a function as virtual, right? And it's very simple. The only thing we have to do is we just put the virtual function right at the front, right? So here we have our eating function, and I say, hey, make it virtual. And what this says, what this word says is, my children, my derived classes, they can modify this function. They can make it better, let's just say, or they can make it more specific. They can adjust it however they please, all right? I give them the power to adjust this function to be different, however they want to do that, okay? So what this says is, if you were to say this out loud, you could say, this is my eat function, but my children can modify it, right? My children can come and tell you that they want to eat different than I do, okay? Let's just say that. So a virtual function can be changed from its derived class. To apply a change, so basically you don't have to, right? The derived class doesn't have to be more specific on that function, but it has the possibility, it has the option to do that if it wants to. So to do that, if you want to change a function that was virtual in the parent, you have to then redeclare the function, right? So the eating function, and then you say, I want to override it, right? This is called a function override. You're saying, the function that's above me, the function that belongs to my parent, forget about it. Don't even think about that one. I'm going to give you a replacement for it. Use mine instead, right? So what this says is, do not use my parents' eat function, use mine instead, right? So you're a rebel child and you're like, don't do what my dad or my mom said. Do what I'm telling you. However, the parent is saying that the child can do that, right? So there's a nice relationship between the parent and the child. The parent can say, yeah, they can modify it if they want to. And then the child can come in and say, I am going to modify it. I'm going to override it, okay? So think about it like that. It's a dispute between a parent and a child, okay? Now, the rest is the same thing, right? So you have overridden the function, which means you have to define it. You have to come here and say, all right, let me change it. So let's just kind of apply it real quick. So let's just delete all these bogus errors that we have, because we don't like errors, all right? And then in my animal class, what I'm saying is, this eating function, right? If you look at the eating function, it just says the animal is eating that many pounds, right? And it's like, okay, well, not all animals eat the same, right? And so you can say, well, this is okay, but it's not good enough. It's not good enough for the dog, let's just say, right? The dog needs to be more specific. The dog would like to say, not the animal is eating. The dog would like to say, the dog is eating, right? I don't want it to be animal. I want it to be dog, right? So let's just say, then you say, okay, well, I would like my children to modify this function, right? I want them to modify it. To do that, we just add the word virtual in the front. Very simple, just one word. Boom. The rest doesn't change. This remains the same. You don't touch anything. The only thing you did is you gave your children the power, or you gave them the power to come here and modify this function that they have inherited, right? Because they're inheriting these members. So now dog, who doesn't have an eating function, right? It doesn't have one because it inherited one. But now dog says, that function that I inherited, I want to modify it. I want to override it because I don't like what my parent did with that function. So to do that, you redefine it. So you say void. So how did it look? We look at animal, we can just copy paste it, right? Exactly the same without virtual. We don't need the virtual. We put that. And then we say, I want to override it. Right? So this says, don't use this function anymore. Use my function. And then we need to define it. So I'm going to go to my animal, to my dog.cpp, and I'm going to define it down here. So I'm going to say this is a void, the returns a void, and then for my dog class, I want to define the eating function, which takes a double parameter called amount, and I define it. And now in here, I'm going to say cout eating like a dog now. All right, you no longer use this code. Now you use this code. You have overridden the logic of this one and added with this one. So now let's just see what happens. I'm going to create I have an animal pointer, so my animal, and I'm going to create a new dog, right? So we're using polymorphism, right? We're storing the derived instance into a base instance, okay? And then let's delete it at the bottom because we want to follow good practices, all right? And then I want to do my animal that eat. My question to you guys is, this is a animal, oh, and I gotta put, let's say it eats 5 pounds, okay. This right here is what? It's an animal pointer, right? So this is pointing to an animal. It's a dog, but it's pointing to an animal, right? It's a dog, but it's pointing to an animal. My question to you is, which function will this eat use? Will it use the animal eat, or will it use the dog eat? What do y'all think? It's a dog, but it is pointing to an animal. So one says the animal. Does anyone disagree or agree? Silence. I take that as you all are thinking. It has been overridden. So here, let me. Here's the dog class. The dog class overrode the eating function that was available in the parent. Right. All right. So a lot of people went with the dog. Okay. So let's just run it, right? So if it says eating like a dog now, even though it's an animal pointer, right? Because this is an animal pointer. It's not a dog pointer. It's an animal pointer, right? But if it says eating like a dog now, then this uses the dog's function. But if it don't fight. Okay, don't fight yet. So here's the thing. 5 extra points on the quiz, or I take 5 points off if it's wrong. So anyways, oh no, okay. Well, that means you guys know the answer. You probably Googled it, or you already know this. Anyways, so it's either going to show this cout or it's going to show this cout, right? So let's just run it. Oh, we got something funky. Oh yeah, remember we were trying to show some. See, we crashed it. Yay, we were trying to crash it earlier, but we couldn't. All right, forget that error. I know, right? Oh, okay. Hold on. What are we doing wrong now? See, that's what we get for messing with errors. Let's see. Oh, okay. Hold on. We left some code from the past. That hey, there you go. -5 for everyone. I like that. I like that. Okay. All right. So eating like a dog now, right? So the other errors that we got, they were related to old code that we left there when we were experimenting with things that we should not have been. Well, no, we have to experiment because we're learning, right? So this thing called the dog function, right? And I emphasize this is the power of polymorphism. Okay, you have a animal pointer. It's an animal pointer, not a dog pointer. And yet, when you call the eating function, it knew to use the overridden function, not the parent function, right? So this is powerful because now you could override the eating function in all the classes that you make. So let's say you override the eating function in cat. Let's just do that. Okay, let's just go here. Let's just show it. Why not? So I'm going to override it in cat as well. So void eat double amount, and I'm just going to say override, right? So cat is overriding the eating function from animal. Dog already overrode it, right? And let's just cheat and use the autocomplete so it's faster. And then in here, I'm just going to say cout eating like a cat now, all right? So one is one is eating like a dog now, the other one is eating like a cat now, right? And then let's just go and then within the same variable, the exact same variable, right? So let's just say I delete it. And I use the same variable, my animal, new cat, right? And of course, it needs parameters. So 1 year old of 10 pound, 20 pound cat, it's a heavy cat. And then I say my animal that eat, right? And it's gonna eat 10 pounds. This is a big cat, and I delete it. All right, so now one was gonna say eating like a dog, the other one would say eating like a cat, right? Eating like a cat, eating like a dog. And so the power of overriding these functions comes that even though you are using the polymorphic ability to treat a derived instance as a base instance, when you call those functions that have been overridden, it uses the derived functions, it uses the overridden functions. This adds more to the polymorphism, because before you can say, look, this variable takes many forms. It first was a dog, and then it was a cat. The exact same variable was a dog, and then a cat. Took many forms. Now we take it to a next step, and we say, look, the eating function, it's this. But the eating function is different when it is a dog than when it is a cat. So the eating function itself is polymorphic. It has taken different forms. You have an eating function that is for a dog and an eating function that it is for a cat. So that has taken different forms, okay? So more power to polymorphism. You can override any virtual function from your parent. If the parent did not make it virtual, you cannot override it. So I cannot, here's another class from animal, right? Let's say get age. Get age is not virtual, which means I cannot try and come here and say int get age, override it, right? It's like, hey, no, you know, it's not a member function declared with override does not override base class member. It didn't even found it because, let's see, did I spell it right? Int get age, but yeah, it doesn't work. So even if I, oh wait, yeah, override, then it's like, no, you can't. So you cannot redefine, you cannot override, I should say. It's not redefining, it's overriding. You cannot override a function that was not marked as virtual in the parent class. Okay, that's illegal. All right. So when we call the overridden function, C++ will use the derived one. That's the little exercise that we just did, right? So this will use the it in dog, but not the it in animal. So here, this is from the perspective of a dog pointer, right? So this is obvious, right? But this one was not as obvious, right? So the eating function from the perspective of an animal, it's a dog. So the question is, do you have to override a function that was declared as virtual? You do not. So let's just, for funsies, since it's a good question. So let's get rid of the cat. Let's just say the cat. We know cats are rebels, but let's say that these ones are not. So I'm going to delete the override, right? So I delete the overridden eat function in the dog class, right? This still works. There's nothing wrong. There is an eating function, right? At least at the minimum, you have the parent's eating function, right? So when I run this, the dog would say eating like a dog, but the cat will use the parent. The animal is eating 10 pounds of food, right? So here, basically, it's just that. It's something simple. Is the cat doesn't have a specific function for eating. It didn't override it. So C++ will say, well, I'm just going to use the parents because the parents provided with that functionality. So the cat didn't use it, okay? And again, that's powerful because you can say, you know what, I'm okay with my parents' definition of eating. I don't need to be more specific. I don't need to add more details to it or change the details to it. Powerful, I know. All right, so the dog class now has to eat. Oh, this is a typo. Has, yeah, discarded. So here it has 2 eat functions, right? So what's interesting though, yeah, so we didn't override the dog. The dog overrided the eating function from animal, but cat did not. So cat, because it doesn't have an overridden function, it uses the parents. Dog, however, did override it. So dog doesn't use the parents, it uses its own, right? it's basically you're not forced to override. You are given the option to override if you want to. How many slides we got? All right, we can finish it. All right. So the dog class now has two eating functions, right? There are two eating functions. Not you. Here is the eating function that was overridden. Oh, sorry. Here's the eating function from the parent, the animal class, and then there's another one, the overridden function, right? So it has two eating functions, right? It has two. We override the parent, but there's still two. We didn't delete the other one. We override it, but we didn't delete it, right? So it has one that was inherited from animal, and another one which was overridden in dog. What happens to the one inherited from animal? We didn't delete it. We overrode it, but we didn't delete it. Well, the answer is that it is still there, but it was shadowed by the overridden one. And so think of it like it's there, no longer has the focus. So when you use the eat function, it uses the one on top, which is the one that was derived, the one that was overridden. What happened to the one we inherited from animal, right? Well, it was shadowed. It got shadowed by the overridden function. And because it got shadowed, it's kind of invisible in a way. You can think of it that way. It's there, but you cannot use it. Well, that's not true, because as you can see the spoiler, can we use it though? Yes, we can. How? We can use it by the child. See, that's why let me see if, is it black or is it good? It's good. Okay, so we can use the parent version within the child version of the function, right? So here's animal.cpp, right? Has the eating function, and it just says animal is eating, right? And then now in my dog function that I overrode, so I override the eating function. In it, I can use my parent's eating function by saying from the animal class, use the eating function and then give the parameter. And now I can say animal eating, but like a dog, right? So I can, let's see, where's Visual Studio? Okay, so here, if I wanted to use, where's my dog? Okay, if I want to use, let's say that this logic right here is amazing, right? The eating function from animal, it's so good that you're like, I want to use it as part of my eating function of dog, but I want to make it better, right? Because remember, inheritance is an extension. So you say, I want to extend the logic of eating in my much more specific version. So now instead I say, I want to use my parent function actually specifies how much I'm eating, right? It tells you how much you're eating, the amount. This one does not. It just says that it's eating like a dog. So I would like that logic to be part of this function, but I don't want to rewrite it. I don't want to copy paste the code. I want to say, use that function. I can use the animal, from the animal class, eat amount, right? I cannot say simply eat, because if I do this, this will use this one. And this becomes recursive, and that's it. You're in a recursive loop forever, and your program will crash. So you're saying, well, if my function of my parent got shadowed by my version of the function, how can I use it? Well, I just say, well, from my parent's class, use the eating function. And then it takes a parameter, so I put the parameter, and now I do that. So now when I run this, let's go back to main. I'm gonna delete the cat, right? So it doesn't show twice. When I run this, what's going to happen is once I call eat, not that eat, when I call this eat, this will say, okay, go to the animal class and call the eating function. This will say the animal is eating this many amount of pounds, and then this will say eating like a dog now. All right, so it should basically mix both functions together. And here you go. The animal is eating 5 pounds, eating like a dog now, right? So you don't have to completely ditch all the logic that your parent function has. You can extend it, and by extending it means use it and then add logic to it, right? So you can think of it as an extension. You can think of it as a replacement. A replacement would be you don't use it. You add new logic. An extension would be you use it and then you add more logic to it, right? So again, the concept of inheritance, it's an extension. It's a much more generic version. It's a foundation, etc. Or you use it like that. Same thing with these functions. So here you go, eating like a dog now. So we don't lose the function, and that's the great thing. So what this says is, hey, use my parent's function here, right? And it calls this logic, so you don't lose it. All right, summary on function overrides, so that we have 2 minutes, so we can do this. We can let the derived class override a base class function by marking them as virtual. Yeah, we can mark a function as virtual in our base class, and that would allow our derived classes to override it. When using the function, C++ will use the object's lowest level version. So it will use the overridden function, right? So we have two eating functions. We have the base and the derived. When you call the function, C++ will use the derived. Now, on purpose use lowest level because we haven't talked about this and we won't really have time to talk much about it. But inheritance, if you recall, I said that you can inherit in a hierarchy. So you can have like one inherits from one, then inherits from another, and inherits from another, which means you can chain also function overrides, right? Think of it as your grandma. She made a function virtual, and then your mom overrode it. And then you say, no, forget my grandma and my mom. I'm going to override it too, right? So this virtual override mechanism transfers also from grandparents and grandparents to the current children, right? So it goes, and then your children could come and say, I'm going to override yours too, because you overrode grandma, so I'm gonna all right, I'm trying to make it funny, but the point here is that this virtual override, it transfers, and you can then say, I'm gonna override what my mom overrode from my grandma's. And then you could also limit that. We won't go too much, at least not now, because we're out of time. But the point here is that I use the lowest level version, meaning the much more specific version. That's the one that gets used, okay? So within the overridden function, you can use the parent version by using base class name, and then you give the function name, right? So summary of polymorphism. Polymorphism allows us to use a derived instance as base instances, right? You can use a dog instance in an animal variable, all right? This is limited, however, to regular variables. In fact, the power of polymorphism is gone when we use regular variables because we lose the derived members. The power comes when we use pointers, okay? Java, C#, they don't worry about this stuff because they use pointers by default. In C++, you have both, so we have to start using pointers from now on. From now on, try to use pointers to get good practice, to avoid memory leaks, and so on. Now, we can treat a data type value as another data type by using typecasting. And I on purpose use data type. I don't use base derived because this could work for anything. Like we turn a float into a dog, even though that makes no sense. We were able to do that. So make sure that the casting is appropriate. Don't do inappropriate castings. So functions in the base class that can be adjusted in the derived class, we mark them as virtual. The derived class can override it and add more code to it. And C++ will use the overridden function instead of the virtual one, right? But you could use the parent one by using the of, what was it? What did we call it? I already forgot the name of the operator, but by saying the function of, or the member of my parent class. All right, that's polymorphism in a nutshell. We will talk about abstract members, which is also related to polymorphism. So we're not done with polymorphism, but the base ideas of polymorphism are here. We're going to add one more thing, which is abstract members. We'll talk about it on Wednesday.